Hello everybody, my name is Tom Hardy, technical trainer, and in today's instructional video covering ECM's, electronically commutated motors, Kyle and I are going to sort of go back and forth. Kyle's going to talk about the PowerPoint deck. Now, we do have an abbreviated PowerPoint deck that we're covering today. However, the entire deck is available as a download under this name. And I'm going to be going over some hands-on stuff. First things that we're going to do is, if we look at the camera down, we're going to see a slew of stuff that we have here. We've got 3 different style ECMs, the motors themselves, and we actually have an inverter here, and this inverter is going to be one that's on a compressor. But the reason that we've got this here is we have an opened up inverter here. This is going to be our constant torque inverter. However, it works the same principle as this much larger inverter. This one controls this motor. This controls a compressor. Now, some of the tools that we need when we're going to be looking at these motors and whatnot. We need a 1/4-inch nut driver. Now, this nut runner or the 1/4-inch nut driver, what we're going to be using this for is to take the actual end bell or the inverter off of the compressor. Now, we do need an adjustable wrench or an open-ended wrench to take off the set screw that this would connect to our blower wheel. And then, of course, we do need a 1/4-inch or 5/16 to pull the blower assembly out. And then we're going to need 3/8 to get the motor mounts off of the actual blower motor, the blower wheel itself, or just simply a 5/16 or whatnot to pull the band off of this. Now, during the testing process, we're going to be using all kinds of different tools. So Kyle's going to talk to you. We got these guys right here, which are the tech mates. We're going to need 2 different kind, or we're going to need one that's going to have the adapters to it. Now, this one here that I've got, this has a 16-pin, so this is going to work with the older style motors, and this one here is going to work with the 4-pin communicating style motors, so I actually have both of those. Now, when we start talking about, we're going to have a section where we go over static pressures and how it reacts and whatnot. We're going to be using this guy right here. This is made by CPS now, but at the time it was AAB. So AAB was, they sold out to CPS, so CPS bought them. So along with this, as you can see, there is no readout on this. This is totally a Bluetooth capable device. So with that, you're going to either need an iPad, iPhone, or a tablet that has Bluetooth capabilities, and we are going to download the CPS link, which is kind of hard to see here, but that's what I have on this one here, CPS link, and there's all kinds of stuff. There's airflow hood, capture hoods, there's velometers, different style of velometers, balancing meters, there's a charging scale, wireless digital manifolds, all kinds of stuff, and it all has them available to you. And there's also pressure temperature gauges that are wireless on there too. Now, I'm not endorsing any particular style. It's just when you see it, it's easier for us to put this on the screen. So when we go down there, we're actually going to have, when we have this loaded up, it's going to bring it up to different styles. We're going to see the gauges on here and be able to run different tests. So for today's demonstration and today's class, it's going to be a lot easier for us to be able to use these pieces because I can tune these right into our mixing board and be able to show that to you on a full screen without any type of glare or whatnot, so you see it perfectly. Now, the other things we're going to need is we're going to need a simple voltmeter or a multimeter. We're going to be using this when we start testing the components of over here, this guy and this guy's, these guys there. And then what that's going to do is that's actually going to show us, be able to ohm out these motors to test them. So let's go ahead and get started. Kyle? Thank you, Kyle. So what we've got here is we're looking at the A97 modulating furnace, and as you can hear, it's ramping up pretty high right now. The fan motor is pulling pretty good amps, and it's actually ramping up into its higher second stage of modulation rate. So our 20-series unit out there is probably hitting about 85–90%, and indoors we know that the fan is running kind of high because we can hear that. Now, let's switch over to the other camera here, and we're going to look at the inside thermostat. So this is our comfort sync thermostat, or comfort sync controller. What we're going to do is we're going to go ahead and get in here, and we're going to start looking at some of the information that we got. So as we're going through this, we're going to be waiting for everything to start loading up. As we can see, our cooling rate is 100%. Let me zoom in here on that. Okay, so we can see that we are 100% on the air conditioner itself. So let's go over to the furnace here. We can see that we're calling for 1,230 CFM. Now, so that's telling us that we're calling for all 3 tons. Let me go ahead and put up a block here, which we can hear it ramp up. We physically know that this machine has ramped up higher, but it's still calling for 1,230 CFM. So nothing more is actually running through there per se, or nothing more is it's not calling for anymore. It doesn't show it doing anymore. But what it's telling us is that our indoor RPMs is 1241. And our power is 91.5%. Let's lower this back down. And we look, RPMs are actually coming, we're going down a little bit. Now we're 1232, now we're at 978. And you can see our power is actually brought down to 60.5%. So that's showing us that as we increase the static pressure just on the return side, it would do the same thing if we were on the supply side because it would still try to overcome that also. But if we look here, we're down to 61% power right now at 974 RPMs. Let's go ahead and bring that back up a little bit. We can instantly hear it. And as we can see, we're actually increasing the power here eventually. Takes a while, there's 62%. We're already up to 1,232 RPMs. We're still at now we're at 92%, but we're still calling for 1,230 CFM. That's our design. Let's go ahead and put a magnehelic on there or a manometer and see exactly what that's going to be giving us. So I'm going to lower this down. Give me just a second and I'll load this up, okay? All right, so now we have the magnehelic or a manometer hooked up to this so we can figure out what our total static pressure is. So while I was doing that, the system decided that it needed to modulate down. So we'll look at the air conditioner real quick here. And it says we're at 95.5% of our cooling rate. So not nearly 100%, so what we do know is that should bring down our airflow, which yes, we can see that it's at 1,176 RPMs, or CFM right now. So we are looking at right now 53.5% blower power and roughly about 933 RPMs. So it has decreased a little bit, and as you can see, our manometer is hooked up. I've already zeroed it out. We have a 0.16 on our return, 0.15, and we have a 0.25 on our supply. Now, we're going to go ahead and reintroduce that power. So if we look on our spec sheets, we're going to take that blower right there, and we're going to compare it and give it us our CFM. So now we're going to introduce more static, which we see the low side climbing up, and we see our high side dropping down just a tad. So now there we are, well over an inch. Right now, if I'm not mistaken, we're going to add that up. We're at 1.09, 1.08 static pressure. And as we look, we're at 1212 CFM, is what it says it's pushing through. We're at 1232 RPM, and we're at 89.5. Now, we compare the before and our after on the CFM table. It's in our blower chart. we see a drastic drop in CFM itself. So if we look back at the air conditioner rate right now, we climbed up a little bit. We're at 98%. So we're going to go ahead and go back to the furnace side. We're still at 1212 CFM. Let's reduce the static pressure again. We can see we're already down to 64% blower power, and our RPM is roughly right now, it's starting to drop, so let's let it settle in a little bit. 964, 968. Still dropping a little bit, but it's not too bad. We're at 59% power also. So there's a quick example of how the blower will change its RPMs and change its power based on static pressure. Now, mind you, it's not overcoming that static, it's just trying to overcome the static. And we can see that our static pressure is back down within the normal range, just shy of 0.4 inches of static. All right, Kyle, back to you.
All right, thank you, Tom. We appreciate that. So let's continue on with a little bit of troubleshooting and then a little bit of tips. And let's talk about air filters. One of the things that gets kind of lost in the sauce, so to speak, is homeowners don't understand what static pressure is. And we want to make sure that they understand that if they go to a store and buy a very high MERV filter, if you get above MERV 8, you need to really look at your duct system and make sure it's sized correctly to do that. So sizing of the filter is important. Make sure we get the correct amount of air, and I'll talk about that in just a few minutes. But it's also really important to understand that we need 600 feet per minute to go through the return. And 600 feet per minute is going to go through that filter. So the filter has to be capable of handling that and filtering the air efficiently at that rate. So, you know, what I'm showing right now is the blue filter that most people most commonly get. And it's better than nothing, but it's not going to get you a good filtering in there. You still get a lot that goes past. But you'll see some of the math we got on here that if, you know, you can look at the math. I'm not going to read through it, but when you go through all this with high velocity, we got 1,650 CFMs going through the supply side with 600 feet per minute coming through the return side. That's a pretty good balanced system. But then if we go to a low velocity filter, or the 300 feet per minute commonly bought by consumers, you see what happens here? We only are doing 825 CFMs. We still may be pushing a lot of CFMs, but what we're looking at here is we're not filtering out all that air near as efficiently anymore. And when we do go and buy the higher MERV filters, you decrease that airflow as well. So it's really important. And on the right-hand side, you'll see where we got the correct size filters for you to look at and put in there. The manual Ds will also tell you what size return to put in there. It'll tell you what size filters. A lot of states now ask you to do that, so that's really important that you get this correct. I know it seems like it's something very simple, but it truly is something that we need to do. So always teach proper filter sizing. So one of the pictures I was telling you about duct work is right here. This is actually, you can see it's an actual installation. This obviously isn't going to work for a lot of reasons, but what we need to make sure of is people understand that ECMs are not the cure for bad duct work. If you got someone that goes in who looks at a job and says, well, this duct work's a little lacking, but we're putting an ECM motor on it, that'll correct it, that is not a good assumption to make. Again, that motor is a good motor. It's going to do you wonders, but it's not going to fix this type of bad duct work. And then there's negligence, just pure and simple negligence. A lot of people don't know, and it's not their fault or anything, but some of them just don't know they got a filter in that system. They'll put it in there, and this is what happens. It looks like this. The filter will pull in, and the coil gets dirty, and then it's a mess to clean up. It can be cleaned, it can be fixed and straightened out, but it's quite a messy job to do. But the ECM motor, again, it's not going to cure this. It's not even going to help it when it gets to this point. So servicing the variable speed, communicating indoor, blower motor, ECM, all the good stuff that we've called it today. You've got the dealer tool belt, the dealer toolbox. You'll see those out there on these motors. There's a lot of good tech literature out there for these. So a lot of good stuff to help you understand and know. So we want to diagnose these motors. So you see the instrument right there, the Tech Inspect. That is something you put in line, and we'll show you that in a little bit. But that's actually to check the motor. Then you have the literature, and you're going to need a good meter as well too. Because on some of these motors, when we get to it in just a moment, you're going to see we're going to talk about DC volts. And so you can't have a cheap meter anymore. You need to have a really good meter with fresh batteries. That it would behoove you to have that. So we want to make sure we got that, and that way we can get good readings. Motor diagnostics, ohms, all the Gentech motors, the dealer tool belt. You'll also see there's dealer toolbox. They change the names from time to time, but generally when you get to the dealer tool in the search bar, it comes up to what you need, and then you can get your literature and everything there. So one thing we want to understand and know is that the line voltage is always present on these motors. Generally, your package units are going to be 240 volts, and your indoor units, unless it's an air handler, is going to be a 120 volts. But what we're looking at here, and you'll notice, this is the 16-pin harness control motor on here. So when we do this and we look at this, communication imports, what should we see? You can diagnose it with our literature. We show you how to do that. There's dip switches and there's various other different ways to do it. One of the ways is just to simply cut, and on 16-pin is just to simply cut the power off, unplug the 16-pin harness, cut it back on, and if the motor runs, then the motor's fine and the program's fine. That motor needs to see that communicating volts there. If it's not there, that module is programmed to run that motor at its top RPM speed or top CFMs. And so if it's running, you know, two things. The motor's running, so that's not bad, and the module recognized and ran the program it was supposed to. We got another issue somewhere. It's either in the plug or it's either on the circuit board itself. So serial communication, this is going to be a little bit different. It's got binary codes that come in here, just like computers, ones and zeros. So it's always communicating back and forth. This is how the 3.0 version can actually match a variable speed compressor's percentage it's running outside. And you see these terminals down here on the picture in the bottom right-hand corner. We'll talk about these terminals and how to check them out. But this binary code tells this motor what to do at all times. So communicating basics right here. The RX, you receive the info from the board itself. So that's the receiving. So you get your operating info. It's going to measure the DC volts between RX and C to prove communication exists, and we're going to show you how to do that in just a moment. Then also you have to have some transmitting, some feedback info. So you get the transmission, the RX going to the motor, and it's ones and zeros, again, binary code, but the TX coming back, that is your feedback to let your board know that the motor is doing what it is supposed to do. The important part to remember about this is you can't put just any motor on the furnaces. That motor has to be programmed for that furnace, or the board is not going to talk to that module on the end correctly, and you're going to get codes on there that it can't see the motor won't start. You'll get a variety of different things that can happen whenever the incorrect motor is put on. And then V is the power, and from V to TX circuit you see DC voltage, and we're going to talk about that a little bit more. But now the built-in test mode, if you apply 24 volts to terminals C and RX, motor will operate approximately 600 RPMs in a counterclockwise rotation. So that's kind of a way to check it. On our boards, there's terminals on there, there's dip switches on there that when you look at the manual, you'll see the dip switches, and you can put, I believe it's dip switch 7 and 8, don't hold me to that, but you can put them in the on position, and it does this right here for you. So it'll prove that it's working correctly. We have other issues if it doesn't. So now we have a choke that's on here. What this choke does is it cleans up the line voltage coming into the motor itself. Generally on our 3/4 horse and 1 horsepower motors is where you'll see this choke. It's important to make sure that the choke is in there for these, because it does reduce peak spikes, current spikes, but it keeps that power clean. Because if you do not have good clean power coming into it, it can interfere with the communication between the board and the furnace itself too. So there's a lot of things in houses now that can cause issues with this. So, but you want to make sure and measure the voltage before and after that choke, and you should see very little to absolutely no difference in the voltage. Now, a lot of people get this confused with the control transformer because it looks very similar. Only the control transformer has 4 or more wires. This has an in and an out. So once you get used to it, it's mounted on our blower housings for the most part on our furnaces. So always replaced if it's failed. Can you jump this out and get it to run? Probably, but it rarely fails. If this has failed, I would look at what happened. There had to be a really bad power spike somewhere. Something had to happen, or if they have a generator on the house or they try to run it with a generator that doesn't have a good sound wave or a good wave to it, it flattens out at both ends. That may take one of these out, and the furnace may not even light off at that point either. So if this choke goes out, something took it out. We need to find cause and effect. What we see is the effect. We need to find what caused it. So we can run a test with a tech inspect. These you can buy, fairly cheap. A lot of technicians still use these. They still want to see this run the motor, and that is perfectly fine. I have no issues with that. I know my counterpart Tom, he uses one. He lives by it, and he believes in it, and it's a good way to check it. That way you can be accurate, and you got a really good knowledge of, is this motor good or bad? Then we can move on to what else caused it. So to hook it up, you need to diagnose the board with the manual, you just hook it up, and I believe Tom's going to show you some of that in a little bit, how to hook this up and how to plug it in, and a little bit more nuances to it than just that. So a little more tips and tricks coming up. If the ECM does not operate with the tech inspect, replace the entire ECM motor and control. While it's under warranty, and I'm going to show you how to ohm this out, but generally the motor never goes bad. You can get the module. So a couple little tips here. With the way parts are right now, if you can't get the whole motor and you can get the module for sure. But while it's under warranty, I would replace both, just in case the windings may have some damage that we don't see yet. It may have weakened it, and you don't want to have to go back out and then replace a motor. So replace the ECM only if available, and that's what I was just saying. And when you want to make sure these things, whenever you turn the shaft or twist the shaft, the way they feel, they got a little herky-jerk in there is what I like to call it. But it's not like what you would see with a PSC motor where you can spin it. It's got a little bit, and that's the magnetic field. That's that rotor. It feels a little different. So it's not locked up. If you feel it catching and bumping, that's perfectly normal. Everything, as long as it rotates freely by hand, we're good to go. When you do pull that off, though, that control module, just like the boards that you see with variable capacitor compressors, those capacitors in there, make sure they discharge. Give it a good 5 minutes before you put your hands inside there and start fooling around. Make sure also when you disconnect the power from the system and you disconnect that motor head, that control module off of that motor, you got a 3-pin connector. Make sure your hand does not come near where that capacitor is. Be very conscious of that. So we want to test measure resistance between each 3 motor leads. Models, well, we got 2.0, 2.3, 2.5, and 3.0. We're only using the 2.5 and the 3.0. So some of the ohms and resistance I'm going to talk about, there's a kind of a wide band here. Well, not really wide, but you can go anywhere from 5 to 20 plus ohms on here, but we'll talk about that in just a moment. So let's look at this. We're actually ohming out a motor right now. So when we're ohming this out, let's take a good look at what we see here. The top one's an open load, the bottom one, the middle one's infinity, and then the bottom one's open. So that tells us these have failed. You know, the resistance between each winding lead and ground should be less than 100,000 ohms. If it's reading open between here and there, these have failed. This is about the only time you'll see this part fail. This failure here was probably due to a power surge, whatever may cause that, a rolling blackout, a lightning strike, whatever. This is what you'll see here. And this is in a rare instance, this motor has actually failed. So test B, you want to read between the leads, and lead 1 to lead 2, 1 to 3, and then 2 to 3. Just like you're checking 3-phase power. Because basically, like we talked about earlier, this is a 3-phase motor. And all the resistance should be plus or minus between 10%. And you can read 20 ohms all the way down to 5 ohms. When you start getting much below 5 ohms, you're almost have a shorted motor out. But, you know, again, remember the plus or minus 10%, and it should be less than 20 ohms. So when we ohm this motor out here, everything looks good, everything passes. It's below the 20 ohms, it's well within the 10%, and you're reading 5.1 to 5.5. This motor passes. This motor is perfectly fine. Now, if we read 1.2 ohms or 1.1 or even less than an ohm, that's when you change the motor out. That's when you make sure, because some damage has happened. And if lightning took out the module, it could have damaged the motor. So when you change out a module, don't forget to ohm the motor out as well too. Again, you don't want to go back to this and say, well, I forgot, sorry about that. So if the motor fails and it's difficult to rotate by hand, replace both of them. And if the motor passes, if the motor module passes both tests, it's easy to rotate by hand, replace the motor control only. And I'm going to tell you, 9 times out of 10, it's going to be that module. But I can't emphasize enough about how important it is to check that motor and ohm that motor out. With that, we're going to take it back to Tom and let him show you some things on the motor.
Thank you, Kyle. So one thing I forgot to tell you about a tool that we're going to need, and a very important tool, is safety glasses. Now we want to make sure that we do have our safety glasses on here because we are going to be using our drills or whatnot. So, you know, our eyes are very important, so we want to make sure we protect them. So, let's go ahead and let's talk about this motor first. Now this motor here, as we can see on the top down, this is going to be our constant torque motor. Now the reason we know it's a constant torque motor is because we have our 24 input controls right here, 24 volt input controls. Then we have our line voltage across the top and our dedicated common. So we got 2 1/4-inch screws here. We got one here and we got one back here in the back. So we got 2 screws there and we're going to go ahead and pull them out. Now I'm going to be using my drill here just simply because of time. So we got 1, we got 2, and we're going to go ahead and take this guy apart. So when we do that, we're simply going to take the motor head or the control itself off and lay it down. Now, we're going to go ahead and pull this. We've got 3 wires in there, a UVW, which is our normal inverter-driven wires. I want to use my phone here to hold that from rolling away. Now, let's look at this guy a little bit closer. So we've got our components that Kyle was talking about. We've got our resistor here, and we've got 2 capacitors. The capacitors are the ones that they're going to show up, and they're going to go open up like a can of Jiffy Pop or whatnot. So when we were younger, we would take the Jiffy Pop, we put it on the stove or the cooktop, it would open, it would bust up, and the top of it would come out like a mushroom. Well, that's what we're going to get here when we're discharging and recharging these capacitors too quickly or too often, where we're trying to over-amp that motor or overtake static issues. So the first check that we're going to do, if we notice that the motor's not running, we checked it out with our tech mates and it still doesn't work. We verify we got 24 volts going to our control on the constant torque one right here. This one does. And so then what we're going to end up doing is pulling this apart. We're going to do a visual check. Now we're going to give it 5 minutes before we go through the whole process, of course. The reason we want to give it 5 minutes is because these capacitors right here are going to be overly charged, upwards to 1,000 microfarads. That's what these guys are at 200 volts. So give it its time, peel it apart, and we're going to be looking right here. We're just going to do a visual check. Are they blown open? Are they expanded? Are they mushroomed or swelled up? If they are, this is the part that's bad. Now on a constant torque, you're going to get it as an assembly, the controller and the motor itself. The other thing we're going to be looking at is going to be the resistor right here. Now this one is almost like a chalk black or a matte color, and it's hard to show up here on this, but it's right there where my finger is. You can see it against my finger, and I'll turn it over, and it's going to be the same place right there on my finger. This one here is about the size of a dime. Now, what will happen is if we're getting voltage imbalances or voltage spikes, or we're bringing too many amps into this machine, this resistor itself will start to have a white charred spot on it, and one of the wires on either side, a wire here or a wire here against the resistance plate, will have actually separated. So we're going to be able to visually see what's wrong here. If we look at this and we don't see anything wrong, we're going to have to go a step further, and that's going to involve our meter here. So we're going to take our meter. Let me straighten it all out here and get my wires ready for it. So we're going to get our meter, and we're actually going to select the lowest ohm value that we have on our meter. Because like Kyle said, we want to be below 20 ohms, but we want them to be within 10% of each other. So what we're going to do is we're going to select. On my meter here, we're going to see that I've got 200 ohms as my selection, my lowest selection. Then we're going to probe arbitrarily just 2 of them. Make sure we get a good connection here. And Kyle was talking about having good batteries in your... So we're roughly about 17.1. Go to the next one. Get a good connection. That one's 13.3. 13.7. And I want to go back to the first one that I had there that showed 17.1, because I know that right now I'm dealing with some dead batteries, and I've also got the long lead here, and we're at about 13.8, 13.7. So we can see there that this actually is a good motor. Let's go ahead and look at the other motors that we've got. So we said we've got 2 other motors. Let me go ahead and pull these guys back down within view of the camera. All right, so here's the 2 different style of variable speed motors that we use. So we have the 4-pin control that Kyle was talking about. This is going to be your 3.0 motor. And then over here we got your 16-pin, which is going to be your 2.5 volt motor. Kyle was talking about how across the top, we're always going to have voltage. Whenever we have power going to that furnace, the power is going to be entering into here. So it's always going to be live on the top set of plugs there, that 5-pin connector. That's where we're going to have our line, our neutral, if it's a 120 volt motor, and our ground. Down here is going to be the input to control this motor, tell it where it needs to be. Now, let's talk about the differences. 16-pin versus the 4-pin. We're going to be using this one here on our A96 furnace, and what that's going to do is it's going to communicate with the board, telling it how many RPMs it's running. Now, we've seen earlier how when we went through and looking at the static pressure, we could tell the RPMs, we could tell the voltage usage and all that. That's going to be displayed with this motor right here. This motor is actually going to communicate with the board, tell it what it's doing, tell it how many percent it's operating at, and tell it how many watts and how many volts it's using. The reason that that's important is so that we can control that motor and bring it down. Like Kyle was saying with the 20s here, we saw how one was working more than the other when we added static to it. Let's talk about the 16-pin one. and then we'll go back to this one again. So the 16-pin one, we're going to be using that on all of our Duquesne and Concord products. So primarily, we're going to see this on our air handlers, the BCE 5V, and we're also going to be seeing this one here on our, we're also going to see this on the 96% two-stage variable speed, and we're going to see it on the 80% two-stage variable speed. What makes this motor different than this one is not a communicating motor. This motor here, what we can do with it is we don't actually need this motor for that furnace to run. If this one was to be bad, we could replace it with a PSC temporarily on a single speed, give the homeowner heat or air conditioning, essentially give them airflow. What we're going to do is we're going to hook it up to the EAC terminal. That's your electronic air cleaner. And inherently, any time that board is supposed to be calling for any type of fan movement, it energizes that EAC terminal, and it's going to let that motor continue to run. You're simply going to put the power leg on that 110-volt motor onto the EAC portion of it, put your neutral on the neutral bar, ground it out, add your capacitor, and that motor and that system will run. If we have one that was supplied with this one, it will not work that way. The reason being is because this motor tells the furnace board what speed it's running. If it doesn't see that communication, it's going to see that there's no motor there. You're going to get that error. Now, this motor is also used on the A97 modulating furnaces and also the BCE 7V, the modulating air handler. Now, let's go ahead and take these things apart. Again, I'm going to use my drill and take out the 2 1/4-inch screws. And I already had one screw taken out there, so I'm going to put all these screws to the side so we don't lose them. Now, when we pull these apart, outside of the fact that this one here is a 16-pin, this one here is going to be the 4-pin, there is no differences, all right? They look exactly the same. If it physically would fit, I could take this head, put it on this motor, this head, put it on this motor, and it would react the same way. They would run the way that they're supposed to, because they both are, they both are half-horsepower motors. Now, physically it doesn't fit because we've got the cooling plates and whatnot, and it's going to hit the back side of the X bracing, so that holds the bearings in, and the magnetics, so it doesn't physically fit. However, if it could, it would run. So let's go ahead and test these out. We see again, we do have our resistor down here. It's going to be right there. It's hard to see because it is the black on black. And then we do have the 2 capacitors. Same thing with this one. The locations is a little bit different. So we have our resistors going to be right in here, and then we do have our capacitors right here. Now, if we angle these capacitors correctly, as you can see on this one right here, that we do have the etching already on there for it to blow open if it has to. So it does have its relief already etched into it. It's going to be hard, you can barely see it about right there. And what that does is that's going to give you your, where it's going to blow open or enlarge and swell in case the capacitor does go bad. Both of these capacitors here, on both of these motors again, these are 1,000 microfarads. So, looking at these are good heads. So now let's go ahead and look at the motors themselves. Let's take this motor and we're going to test it the same way. Go leg to leg. This one's going to be roughly about, it's going to end up at about 10.4, 10.5, 10.6. We'll go to the next one. 10.7, and we'll go to the last one, the last combination that we got. Let's get some wire, make sure we got good connection there. I'm using needle nose, so it's kind of hard to get a really good connection in there. There we go, 10.5, 10.4. So what that's going to do is that tells it that this motor itself is good, and we could go through the same process on this one. let's explain how our tech mates work. So I have two different tech mates here. The first one I'll do is I'll talk about the 16-pin one. Now, Kyle talked about how there's different ways to be able to test these. One of the ways is to use the tech mate. The reason I use that is because, well, I bought the tool a long time ago. Now, let's say that this motor's hooked up. All right, this motor's hooked up to the head and it's into its spot. If we simply take this 16 pin off of the board, this motor, and we have power going to it, this motor should start because of a safety circuit inside of it. One of these 16 pin wires, or a combination of one of these 16 pin wires, what happens is it's like a limit. So if that limit circuit is opened up, primarily the high limit or the low limit, or the high limit or one of the rollouts, what will end up happening when we pull that off, it does not have that circuit completed, that motor is going to run. And then thinking that there's an error, it needs to cool down. So it's going to run that motor. If that does work, and we're still not able to get the motor running under normal operations, that means our controller or our board is bad, not this controller. Now, if we don't have that, if we want to go a step further, we can hook this in. Now we're definitely going to have power to here, and this is going to be hooked up to our motor. Then we're going to be bringing in our TechMate control. Now to power this TechMate, we got two different wires here on alligator clips, and we're going to take those two wires and we're going to hook it onto the R terminal and the common terminal. Then we're going to see a light come on right here. So the green LED light's going to light up, and it's going to tell us that we do have power. And then we can simply go through here, give it a G call, turn on high heat, turn on a call for cooling, Y1, Y2, and then we can give it a no call, dehumidification. So that's going to give us a dehumidification call down here or a no call up there. So that's how this one works. So let's set that off to the side. Let's look at the other size, the 3.0. Now the 3.0 can't be used that. They also do have adapters for them, but I have a separate little TechMate Pro for this one. Now this one, obviously, this is going to get hooked up to the red terminal. And we do have a black one here that's going to get hooked up to the common terminal. Now, we do have a set of wires that come on here, and as we can see, we've got 4 pins here. We're going to simply take that, hook it in. Now, we're going to do the same thing, except this one just has a simple on-off. So we'll just turn this on. The motor should take off and start running. Turn it off, it should be off. When we have our power, we're going to have a little light right here telling us that it's ready to go, and we simply just turn it on. Now that motor should start. If that motor does not start, we need to start looking into this. Now, what's really good is on our gas furnaces, if we look at these heads, let me get this back out. If we look at these heads and we determine that the head is a problem, we see this blistered open and we see the resistor that's blown, or we see the resistor that's blown or charred, what we can do then is we can actually replace this if the motor itself tests good. So if the motor tests good, we can replace these on a gas furnace. Where can we not replace these only? Constant torque. So if it's the constant torque style that has this style head on it, we have to replace the head and the motor together. Or if it's a 240 volt application. So it's going to be on a if it's on a package unit with the AC and electric heat coils, or if it's on a package unit that's a heat pump, we're going to replace the motor and the head together. Now, if it's on an air handler, motor and head come together. Gas furnaces with 110 volt application, heads are separate than the motors. We can replace them to keep the cost down. So, hopefully everything was good for you on this and we got to be talking about this. Now, we're also going to get into this a lot deeper on our 5-minute videos, so pay attention and look out for them. With that, I thank you. Thank you for your time. Please make sure that you put this in your app, the installer portal, that this is a class taken. If you do teach this class or assign this to any of your contractors, please, at that point, put it down as a class given. Thank you. Have a great day.